Okay, hello everybody, and thank you for inviting me to give a talk in QNLP 2020. And I'm going to talk about near nonlinear copying of vector spaces. So I'm going to explain what that means and applications to natural language processing. This is hugely joint work with my PhD student, Laklang Makfit, Hadi Wazni, with whom I worked in Queen Mary as a master's student, and then we've carried on working together, and of course, Gijs, doing PhD with me in Queen Mary, and now in Utrecht, Adriana in Utrecht, and Alexis, who everybody knows now by now, is in Oxford doing a PhD. And we would like to thank the adjoint ACT School of 2019 because part of this came out of a joint project there. Okay, so I'll start with the NLP applications, and I want to motivate something which we've called the Discourse Challenge. So the idea is that if you want to reason about natural language without taking discourse into account, so you have separate, isolated sentences, and then you want to develop an automatic procedure that will tell you if these sentences, firstly, are grammatical, and then secondly, based on their grammatical structure, develop a vector representation for their semantics, for their meaning. And I'll, like we heard in the previous talk, and I'll motivate this towards the end of the talk, vector spaces are very good because you can then run a very nice, easy learning procedure and then learn meaning representations using large corpora of data widely available on the internet these days. So following an idea by Lambeck, in order to analyze the grammatical structure, we work within an algebra of a residuated monoid. I've put a signature there. This is a partially ordered monoid, multiplication dot, it's unit 1. And then the multiplication is non-commutative, so you've got left and right residuals, one for each argument, which we denote by forward and backward slashes or left and right arrows here. So you fix a set of basic grammatical types in a set B. Examples are N for noun phrase, S for sentence. And then you generate a residuated monoid over this set B. I've denoted it by T of B. And of course, in this generated residuated monoid, you have got many, many more types other than the basic grammatical types N and S. You've got multiplications of them, residuations of them, and then multiplications of the residuations, and so on and so forth. And then when somebody gives you a sentence like John slept, think you're a machine. You know all about residuated monoids, so you have access to all the partial orders of the setting. You can check that quickly, automatically. And then you've got access to a dictionary, a lookup table, where you can go and take out, extract the type of each word of language. So if somebody gives you the sentence John slept and asks if it is grammatical, you go and look into a dictionary, take the type of John, which is a noun phrase N, take the type of slept, which is an intransitive verb, and forward arrow S, N to S. And then what you're going to check is whether the multiplication of these types, N multiplied by N forward slash S, reduces to is less than or equal the type sentence S. If that's the case, then you say John slept is a grammatical sentence. As you can quickly verify, this is indeed the case here. So just with this strategy and a clever assignment of types in your dictionary, you can cover a reasonable fragment of many different languages. But if you go from the level of isolated sentences to discourse, where you have a set of sentences, a collection of sentences that are related to each other via phenomena like anaphora, ellipsis, question answering, dialogue, then this setting is going to fail. I would like to say drastically, but it will fail. Why? So consider a very simple discourse. John slept, he snored. Here, these two sentences are linked to each other via anaphora. He is a pronoun. Is referring to a noun phrase, the noun phrase John, that is occurring before it. And this link, this reference has to happen in the grammar in order for the reduction of these two strings be S multiplied by S. So you have two sentences concatenated with each other in this setting. And what you want your machine, your automatic procedure to do, so if you give it this discourse, John slept, he snored, it has to tell you that it's the multiplication of these two types, S with S. But a quick check shows that this doesn't go through. So John is N, slept is N/S. He is a pronoun that is referring to an MP before it, so it's of type N arrow N. And snort is another intransitive verb. And if you multiply these types, you can quickly see that this doesn't reduce to S multiplied by S. Now, building on the work of Lambeck, many people try to solve this problem, and I refer to the work of Glenn Murrell, who said, in fact, you can copy the type of John, N, to N times N, and then you can permute one of these copies from before slept to before he, so you go cross sentence boundaries, and now you can check that the reduction on the last line of these slides works perfectly well. The multiplication of these types after copying and moving is less than or equal S times S, two sentences referring to each other. Nice, but if you want to work in a theoretically firm setting, there are at least three problems. Problem one is that in a residuated monoid, we don't know how to copy. Formally, we don't have that N is less than or equal N times N. We don't know how to move. We don't have that N times B for B an element of this monoid. This is not less than or equal B times N. And then if I'm naive and I add these two axioms to my residuated monoid, and I say, I just want the residuated monoid up to these two axioms to be able to analyze discourse, the setting will hugely overgenerate. So I'm not going to go through the details of this, but you can check easily that things like John slept, he hit he, or hit a transitive verb, then you can show that this is in fact a multiplication of two grammatical sentences, which is not the case. So there have been solutions around building on the work of Mikhail Mortkart, also jointly with Cullen Muriel, on controlled operations on top of Lambeck calculus, the residuated monoid settings. So if I look at this very naively, interpret it algebraically in a very naive way, I'm working in a model residuated monoid, where I have my normal monoid, and then I add this diamond operator to it. And I'm going to ask only for diamonded types to be copyable. So diamond A is less than or equal diamond A dot diamond A, and only diamonded types can be permuted. So diamond B dot A is less than or equal A dot diamond B, for example. And then it relies on the person who's assigning these types to be a good linguist and to put the types in the right places in the dictionary, in the lookup table. So that's going to work. You can go and check. I won't go into the details. But then the second question is that we've made the passages from grammatical settings to vector spaces through the use of category theory. So we want to make this model residuated monoid, or my naive interpretations thereof, into a nice categorical setting. So we start with the categorical interpretation of a residuated monoid, which is a monoidal by clause category. You've got a tensor and its unit I. Because it's by clause, so you've got two internal homes and those two evaluation and two Coring morphisms satisfying the normal equations. What we're going to add to this is what's known as a coalgebra modality. So for each object, so this coalgebra modality we denote by bang, and each object bang A has a comonoid structure on it, delta A and EA. Delta A is a co-multiplication and EA is its co-unit. And so these structures, if you work with categorical semantics of linear logic, you've come across these. If you've come across the work of Silly, Coquette, and Blue on differential categories, you've seen these coalgebra modalities. The difference, one of the differences is that we don't have much of the structure that's going on in linear logic, so you don't have a byproduct. We don't work with them here. But also more importantly, the main difference with differential categories is that the base setting for differential categories is a symmetric monoidal closed category, whereas here we're going to add restricted symmetry morphisms, where the banged objects can be moved from before the tensor to after the tensor. And I've denoted this underneath with sigma R and sigma L. Now you can ask Lachlan in the Slack channel, who knows much more about the details of these categories. They satisfy some other conditions, but on the logical side, and that's what we did in our ACT 2020 paper, is that we found out that this categorical setting, which I call relevant categories. This is sound with regard to a logic called Bangal star, which is Lambda calculus with a relevant modality, developed by Kanovich et al. So I've just showing you very quickly the Gensen style sequence calculus of the logic. You've got Lambda calculus with the slash left and right operators, to which you're going to add a bang modality with its own left and right rules, permutation, and more importantly, contraction. So we showed that these are sound with regards to relevant categories. On the semantic level, what we want is an instantiation of these relevant categories to the category of final dimensional vector spaces and linear maps. The problem here is that FD-vect is symmetric compact closed category, so you've got your restricted symmetry morphisms, but it's not a relevant category. You don't have a coalgebra modality on it, unless you think of it in the following way. So you have a functor f, a free functor from FD-vec over a field, let's say R, two tensor algebras over R. This is a free functor. It has a left adjoint U, which goes from the algebras over R to category of final dimensional vector spaces on R. And then if you compose these two, F and U, you're going to get a monad from FD-vec to FD-vec. Dualize the monad, and then you get your desired comonad, which will give rise to a coalgebra modality. Now, question is, what is F? So normally, F is the bosonic Fock space or the symmetric tensor algebra over a vector space V, but this is infinite dimensional. We want to make it finite. A simple way of going around it is to work with the fermionic Fock spaces or the antisymmetric algebra, where you quotient the n-fold tensor by Lewis equivalence relation. Now, I won't go through the details, but you can look it up on Wikipedia as I give the rest of the talk, or you can ask Lachlan in the Slack, he'll explain. So the UF is going to give you a monad, you dualize it to get a comonad, and work with the dual of the multiplication map to get a co-multiplication map. It's a complicated operation, and I haven't understood it yet. My understanding is that whereas UF is an operation, so the multiplication over the tensor algebra concatenates at different layers, layer-wisely. Its co-multiplication is dual, has to separate, break, and then you can do this in many different ways. I don't know how to do this in the absence of a join operation. Lachlan has a much nicer way of explaining how this becomes untractable very quickly. So we have to understand this to develop a co-multiplication map. Then again, in the absence of this, we've worked with a very simple idea. So for the examples that I've shown you, you only need two copies of a vector space. So let's project to the second layer of this fermionic Fock space. And then just be very naive, fix the basis. So assume this vector space V, which we work with, has basis, EI. And then you have your normal basis copying operation, half of the Frobenius bialgebra that sits on finite dimensional vector space with a fixed basis. So you have EI tensor EI, which we call basis copying. So you get a copy of the basis. And if you look into the co-multiplication or co-free coalgebras on vector spaces, you'll very quickly come across a literature known as graded algebras or K-algebras. So inspired by that, we've also extended this basic copying to something which we call a K extension. So instead of just tensoring EI with itself, you tensor EI with K. K is a real number. So here you think of it as a vector of number K plus K tensor EI. So we go through the details of this construction in our SemSpace paper. And you can generalize this to any layer. I won't go through this. And let me just show you some examples. So we have the anaphora example. John slept, he snored. You can nicely, using the clasp diagrams, show that John is being copied. You have two copies. One is going to be fed to slept. One is going to be moved over and be fed to he, the result of which is going to be fed to snored. Very soon, if you try to calculate these things in all details, you'll see that when you copy the basis of the vector corresponding to John, Ci and I, then you get two copies of the basis, and you have to decide what are you going to move to the site of he. Are you going to carry on the Ci's to he or keep it at the John site? So if you keep it, you'll get sleeps, John, tensor, snores, Ni. So this Ni is the same as EI of previous slides. Or if you decide to just keep the basis at the site of sleep, you can move a full copy John to he, and you get the second line, sleeps some of an I, tensor snores John. So you get two options if you do the basics copying. In the K extension, things are much more elaborate. You don't get two options, but a sum of these two options together, which I've shown down there. And what's very nice and an achievement or a result of its own, and we again go through all the details in some space paper, is that whenever you work with discourse, you have anaphora, you have ellipsis, and your theoretical linguist is going to immediately ask you, how about cases where you have anaphora and ellipsis? This will immediately lead to an ambiguous situation. And then you have at least two readings for the examples I'm going to explain in a second, strict versus a sloppy interpretation. So you have John ran his code, Bob did too. So this has two interpretations. John ran John's code, Bob ran John's code, or the other interpretation says John ran John's code and Bob ran Bob's code. So when you read this sentence, both of these interpretations should come into your mind. And accordingly, your model has to have two distinct vector representations for the two different readings. And for the first time, I've been working on this discourse challenge for quite a few years. And for the first time, this formalism can actually model strict versus sloppy readings, both in the basis copying and in the K extension. Okay, I'm going to spend a few minutes to explain some experiments. So we start with distribution semantics, originated in the ideas of First and Harris, where you sort of turn your large corpus into a vector space based on the co-occurrences of the words with each other. So here, the word file can be close to the vector representation of file can be close to the vector representation of smooth or register. Now, file is an ambiguous word, verb. If it's close to smooth, you know that in your corpus, file had mostly the smooth meaning, like filing a nail. But if it is closer to register, you know that in your corpus, you can also think of it as in your paragraph, in your sentence, file had the register meaning. And Schutz has, in his seminal work in 1919, he has shown that vector space as the distributional model has very nice applications to disambiguate these such words. And later, in a large body of work, we showed that, in fact, if you extend the disambiguation problem from the word level to the sentence level, you're going to get much better results. And this builds on work of Lapata and Michel and Lapata. So here the idea is that if you don't look at smooth in isolation, but in sentences like young woman filed her nails and local government filed its accounts, then you can do the disambiguation much better. But of course, here you have to build representations for the sentences rather than just for words. And it's better to take the grammatical structure of the sentences into account. So you build representations for woman file nail. And if it is closer to woman smooth nail, you say that in that sentence, the smooth file meant smooth. You build the representation for government file account. And if it's closer to government register account, you say that file meant register. So we have been experimenting with extensions of these data sets to sentences that have elliptical phrases in them. So we developed a data set in NACL 2019 with Gijs Weinholz. So instead of just having young woman filed her nails, you have young woman filed her nails, my mom did too. And obviously this in this sentence is much more clear that file doesn't mean register, but it means smooth. In ACT, we extended these models to sentences that are parasitic gaps, parasitic gap phrases. So you have nails that woman filed after cutting. And the idea, so we run experiments, right? You build vector representations for pairs of sentences in these data sets. And there are at least two goals for this experiment. One is that you want to see which one of your near nonlinear copying operations, K extension or basis copy, works better, and which one of them comes close to this full nonlinear copying operation when if you have a vector, you don't care about the categorical semantics underneath, and you just copy the vector, V goes to V tensor V. So you have two full copies. of your vector. So you want to see if you don't want to have nonlinearity, you want to have a firm categorical semantics underneath, which one of your linear copying models come close to the nonlinear copying model. That's like goal number one. And if you can see, we work with 3 sets of neural word embeddings: BERT, which is the state of the art, FastTech, and then word2vec, which is the first generation of these neural embeddings. And you can see that actually you're quite safe. The K extension and basis copying, all the models do come very close to the nonlinear copying operation. So that is really nice. The second goal is that to see these sentence representations that are built using explicit grammatical information from the sentence, which one of them can beat the state of the art neural sentence embeddings. And you see that we do beat word2vec, we do beat FastTech, we don't beat BERT. No, BERT's like a model with millions of parameters. It's been trained for months over large warehouses of computers, but I think, in fact, as I can show in the last slide here, there are some hopes. So what are we going to do next? First of all, we don't need many copies of things, so we don't need to work with a full version of the relevant modality. We can work with bounded version of it and then get decidable logics. Proving completeness is a challenge, but we have some ideas. We want to repeat these experiments for sentence similarity and inference. I've listed some data sets. And then one nice thing is that we know that these experimental results can be improved. So I'm actually hoping we might be able to beat BERT. And this is based on our recent paper in QNLP 2020 with Gijs and Stephen Clark. And that you can actually learn the functional types of the Lambert calculus using neural nets. And if you do so, you get really close to state of the art, and you might as well beat them, fingers crossed. Thank you.
Thank you, Mehrnoosh. Thank you for a really nice talk. So Dawood is asking on the Slack channel, so does this grammar handle ambiguity in the referent? So he gives an example. John went to school with Bob. He forgot his lunch.
Okay, so when you analyze the grammar, you have to make some decisions, what to copy and where to copy it. So it's a design problem for the person who picks up the types from the dictionary and decides what to copy and what to move where. If you have that level of intelligence, yes, then you can deal with ambiguity. Automatically, not yet, no. You have to think of putting some kind of mechanism on top of it.
Yeah, so I guess this is kind of related to like, how do you parse? So this grammar has different parsings in different cases, right? So actually one question about so with this grammar with a modality, how hard is it to parse? So is there a complexity of parsing, and what's the amount of choice that's involved in the parsing process?
Yeah, these logics are, we've worked very naively with them. So you just copy and move. You can mark what you can copy, and you can restrict some overgeneration by using the bangs in a clever way in the dictionary, and you can hope that you can learn these types automatically. But then they are highly undecidable. So it's very hard to come up with the right amount of correct parsers in a reasonable time. Well, our hope is that if you, instead of working with like many copies of a type, you can bound it. So you say, I'm just going to work with 5 copies. And then the hope is that they're going to become undecidable. And there's only a few cases you can have, and then you go through them and pick out the right ones.
Thank you very much.